This is my fifth video lesson for Unit 12. In this lesson, we'll be calculating the equilibrium concentrations and constant K. Go to page 22 in the class packet. Keep in mind, this topic is not on the chemistry Regents exam. Motivation, given a reaction not at equilibrium, see table. When the reaction reaches equilibrium, will more reactants be made or products? So here we're given a reaction, A and B are reactants, C and D are products. We are given the initial concentrations of the reactants. Currently, there are no products. This is the initial concentration of the reaction not at equilibrium. So when the reaction reaches equilibrium, will more reactants be made or products? Since there's no products to begin with, as the reaction approaches equilibrium, products will be made from the reactants. Since a reaction at equilibrium typically have a mixture of reactants and products, so the reaction will shift right towards the products as the reaction approaches equilibrium. Learning target. At the end of the lesson, I'll be able to use the RICE table to solve equilibrium problems, concentration, and constant K. Homework will be number 5, which will be based off this lesson. In task 1, we will be focusing on how to set up a RICE table, also known as the Rice table. In the previous lessons, we were given a reaction at equilibrium with the equilibrium concentrations. This time, we are not given the equilibrium concentration, but we're given the initial concentration. So the purpose of the Rice table is to figure out the concentrations at equilibrium. You can also figure out the partial pressure at equilibrium if you're given the initial partial pressure. Rice is an acronym. R stands for reaction, I stands for initial amounts, it can be concentration or partial pressure, and C stands for change, the change in concentration or partial pressure, and E stands for equilibrium, which tells us the concentration or partial pressure at equilibrium. So the goal is to get the values in the last row of the Rice table. The first step, whenever you come across a question asking for the concentrations or partial pressure at equilibrium, if you're given initial amounts, is to draw or set up a Rice table, like this. Next, you want to write the chemical equation in the first row, with each substance aligned with each column. Since there's 4 substances, there'll be 4 columns. Then, from the question, look at what is given. Are you given concentration? Are you given partial pressure? Whatever initial amounts you're given, write it in the second row. If a substance is not mentioned or is not given to you, assume it's 0. These amounts are not at equilibrium. I'll be using the amounts from the motivation as an example from the first slide. So here are the initial concentrations of the reactants and products. The next step is to figure out which direction the reaction will shift as the reaction approaches equilibrium. Will it shift to the reactant side or product side? Will there be more reactants or products at equilibrium? At equilibrium, there is typically a mixture of reactants and products. So if you look at the initial concentration, there is no products, but there is reactants. Therefore, as the reaction approaches equilibrium, more products will be made from the reactants. Therefore, this reaction will shift right or shift to the product side to make more products. So whenever you set up a Rice table and you see one side of the reaction has zeros, the reaction will shift towards that side. Now that you figure out which side the reaction is shifting, we can now fill in the change row. In this example, as the reaction approaches equilibrium, there will be more products made from the reactants. Therefore, the amount of products will increase, so it will have a positive change, and the amount of reactants will decrease, therefore will have a negative change. Since A is a reactant, it will have a negative change, and X represents the amount of change. We must also keep in mind the mole ratio of each substance in the chemical equation. Therefore, we have to include the coefficient into the change. So A has a coefficient of a lowercase a. So we're going to include it into the change. So for A, it will be minus AX. For B, since it's also reactant, will be minus BX. C and D are products, so they will have a positive change. C will be positive CX, and D will be positive DX. These variables represent how much the initial concentration change as the reaction approaches equilibrium. One of the goals of the rice table is to figure out the value of X so you can figure out the concentration at equilibrium. To get the last row, you'll be combining the initial and the change. So for example, for the equilibrium concentration of A, it will be 1 minus AX. For B, it will be 2 minus BX. For C, it will be 0 plus CX or CX. For D, it will be 0 plus DX or DX. So here are the equilibrium concentrations of A, B, C, and D. To figure out the value of X, we will need the value of the equilibrium constant. Here's the equation for the equilibrium constant, which represents the ratio between the products and reactants. Make it a habit to write out the equilibrium constant K's equation. Once you write out the equation, you can plug in the equilibrium concentration into the K constant equation. So if you're given the value of the K constant, you can figure out the value of X. Once you get the value of X, you can plug it in into this row and get the values of the equilibrium concentration of each substance. To help you illustrate how does the rice table work, we will be looking at two simulations which is built upon the simulations from page 16 in your packet. If you recall, this is the reactant and product at equilibrium. Initially, we're given 14 reactants and 0 product. The K constant is equal to 1.33. At equilibrium, there was 6 reactants and 8 products. So this is what we figured out in simulation number 1 on page 16. So let's say you were not given this information. You were only given the initial amount and the K constant. Can you figure out the amount of reactants and products at equilibrium? You can use the rice table to do that. Initially, we have 14 reactants and 0 products. Since there's 0 products, it will shift right. So the change for the reactant will be negative X. The change for the product will be positive X. X represents the amount that was changed. So at equilibrium, the amount of reactant will be 14 minus X. The amount of product will be X. The next step is to figure out the value of X. To do that, we need the K constant. The value of the K constant for this reaction is 1.33. Next, we set up the equation for the K constant. K is equal to 1.33, which is equal to product over reactant. So it'll be X over 14 minus X. Next, we use some algebra and solve for X. X is equal to 8. Once we get the value of X, we can plug it in back into the equilibrium concentrations of the reactant and product. For the reactant, it will be 14 minus 8, which is 6. And for the product, it will be X equal to 8. This is the equilibrium concentration. Notice it is the same as the equilibrium concentrations we figured out from before. Now let's look at the second simulation. If you recall, we were given 4 reactants and 10 products. But this time, we do not know which direction it will shift because neither the reactant or product is 0. Mathematically, it does not matter. You will get the same answer regardless, even though C will be the opposite sign depending on which direction you shift. I will prove it to you by showing you both directions. There is a correct way of determining which direction it will shift using Q. We will discuss Q in the next lesson. Let's say the reaction will shift right to the product side. So reactant will be negative X, and the product will be positive x. So for the equilibrium concentration, for the reactant will be 4 minus x. For the product, it will be 10 plus x. We can now plug this in into the K constant equation. K is equal to 1.33, which is equal to products over reactants, so 10 plus x over 4 minus x. Using algebra, we get x is equal to minus 2. We can plug in the value of x into the equilibrium concentration. For reactant, we have 4 minus x. 4 minus negative 2 is the same as 4 plus 2, which is equal to 6. For the product, it will be 10 plus x, so 10 plus negative 2 is 8. These are the equilibrium concentrations that we figured out from before. Let's say instead of shifting products, we shift reactants. We will get the same answer mathematically, as you can see here. This time, we get x is equal to 2, and when we plug it into the equilibrium concentration, we get the same answer. For task 2, we will be looking at 3 different scenarios of the type of questions involving rice tables. So for the first scenario, if possible, take the square root of both sides to get the value of x. Let's look at the first question. The initial concentration of H2 and I2 are 0.2 molar and the K constant is 64. Find the equilibrium concentration of all species. So here's the chemical equation with H2 plus I2 gives us 2HI. In the beginning, we're given the initial concentration of the reactants of H2 and I2 of 0.2. Notice we are not given the concentration of HI, therefore it is 0. This is the initial concentration. Notice there is no products. Therefore, as the reaction approaches equilibrium, the reaction will shift towards the product side. For a change, there will be a decrease in reactants and an increase in products. Since both H2 and I2 have a coefficient of 1, the change for both of them will be minus x. And since HI have a coefficient of 2, the change will be plus 2x. To get the equilibrium concentration, we combine I and C. So for H2, it will be 0.2 minus x. For I2, it will also be 0.2 minus x. And for HI, it will be plus 2x. To figure out the value of x, we have to use the equilibrium constant equation. It is best to write it out. K is equal to HI squared over H2 times I2. We can now plug in the equilibrium concentration into the equilibrium constant equation. From the question, we're given that K is equal to 64. Now we have to solve for x. The easy way to do this is to take the square root of both sides. Sometimes you cannot take the square root of both sides. If you cannot take the square root of both sides, you have to use the quadratic formula or the 5% rule approximation. I will show you how to use them later. After you take the square root of both sides, you can use algebra to solve for x. You get x is equal to 0.16. Once you get the value of x, you can plug x in into the equilibrium concentration to get the value of each substance. So for HI, it is 0.32 molar. For H2 and I2, it is 0.04 molar. These are the equilibrium concentrations and the answer to this question. For learning check number 1, given this question, what is the value of x? Pause the video, resume completed. X is equal to 1.69. Let me show you how to do it. The first step is to draw the rice table, fill it in. Next, you set up the K equation, HF squared over H2 times F2. Next, you plug in the equilibrium concentration into the K constant equation. Based off the question, K is equal to 115. You take the square root of both sides and solve for x. X is equal to 1.69. To find the equilibrium concentration of all the species, you plug in x into the equilibrium concentration. HF has an equilibrium concentration of 3.37. H2 and F2 is 0.31. In this question, we cannot take the square root of both sides. Therefore, there are two ways to approach this, either using the quadratic equation or the 5% rule approximation. I will first show you the quadratic equation. In this question, the initial concentration of HCN is 2 molar and K is equal to 0.001. Find the equilibrium concentration for each species. The first step is to set up the rice table. Here's the equation. For the initial concentration, HCN is 2 molar. We are not given any of the other ones, so they are 0. For H2O, we don't really care because it's not even going to be in the K constant equation because it is a liquid. So we're going to ignore H2O. If we look at the initial concentration, we currently have no products. Therefore, as the reaction approaches equilibrium, it will shift products. For change, HCN will be minus X, and for each product, it will be positive X. For the equilibrium concentration, it will be 2 minus X, and for each product, the equilibrium concentration will be X. After we set up the rice table, we can now write out the equilibrium constant equation. Always write it out. Next, you want to plug it in the equilibrium concentration into the K constant equation. In the question, K is equal to 0.001. Notice we cannot take the square root of both sides. Therefore, we will be using the quadratic equation. After using the quadratic equation, we get two possible values of x. X is equal to 0.0442 and x is equal to negative 0.0452. Since in the rice table, the amount of reactants are decreasing and the amount of products are increasing, x equal to 0.0442 makes more sense, since it illustrates that reactants will decrease and products will increase. After we get the value of x, we can plug it in into the equilibrium concentration. We get HCN as equal to 1.956 molar. Each product will be 0.0442 molar. These are the concentration at equilibrium for each substance. For the 5% rule approximation, it is easier than the quadratic equation because it requires less math. There is limitations though. For the 5% rule, you can only use it if K is very small. K has to be less than 1. If that is true, you can ignore x when there's a number subtracting x, as you can see here. The reason why you can do this is because if K is very small, the change in concentration, which is x, will also be very small. So a number minus a very small number will be about the same. So if we ignore x over here, this will be equal to x squared over 2, equal to 0.001. Since x is very small, when 2 minus a very, very small number, that will be about 2. This is the approximation. Once you do it, you can solve for x. You get x is equal to 0.0447. This is much easier than using the quadratic equation. Once you get the value of x, you can plug it in into the equilibrium concentration. For HCN, it will be 1.955 molar, and for each product, it will be 0.0447 molar. If we compare the answer with the answer that we got from the quadratic equation, you can see that the answers are very close. To double check if we can use the 5% rule approximation, we have to check if the error is less than 5%. To do that, we're going to use this equation, x over the initial concentration times 100%. If that is less than 5%, we can use this approximation. If that is greater than 5%, we cannot use this approximation, and we have to use the quadratic equation. So x is equal to 0.0447, and the initial concentration was 2. Using this equation, we get 2%, and since 2% is less than 5%, we can use this approximation. Learning check number 2. In this question, what is the value of x? Pause the video, resume is completed. The answer is choice 1. Let me show you how to do it. The first step is to set up a rice table. Since the initial concentration of the products is 0, the reaction will shift to the product side. The equilibrium concentration of CoCl2 will be 0.095 minus x, and for the equilibrium concentration of each product, it will be x. The next step is to write out the equilibrium constant equation. The equilibrium constant is equal to 2.2 times 10 to the minus 10. Since k is very small, we can use the 5% rule approximation. 0.095 minus x, since x is very small as well, this will be approximately 0.095. Next, we cross multiply and solve for x. We get x as 4.5 times 10 to the minus 6. To double check if we can use this 5% rule approximation, we plug it into this equation, x over the initial concentration times 100%. Since it's less than 5%, we can use this approximation. Once we get the value of x, we can plug it into the equilibrium concentration to get the concentration of each substance at equilibrium. For the last scenario, we'll be finding the value of the K constant. Let's look at this question. You have 1 mole of NH3 that is sealed in a 1 liter container and is heated to 500 K. Calculate the K constant if the equilibrium for the concentration of NH3 is 0.58 molar. The first step is to set up the rice table. Since we have 1 mole of NH3 in 1 liter container, the concentration of NH3 will be 1 over 1, which is 1 molar. In the question, we are not given the initial concentration of N2 and H2, so they will be 0. Since the products have 0 concentration initially, the reaction will shift to the product side, so the change for NH3 will be minus 2x, the change for N2 will be positive x, the change for H2 will be positive 3x. The equilibrium concentration for NH3 will be 1 minus 2x, for N2 it will be positive x, for H2 will be 3x. Notice in the question, they tell us the equilibrium concentration of NH3. It is 0.58. So we can set 1 minus 2x to be equal to 0.58. We can solve for x using this equation. So x is equal to 0.21. Now that we got the value of x, we can solve for the value of the K constant. The next step is to set up the K constant equation. K is equal to N2 times H2 cubed over NH3 squared. We plug in the equilibrium concentration into the K constant. Next, we plug in x into the equation. We get K as 0.16. Learning check number 3. In this question, what is the K constant value? Pause the video, resume is completed. The answer is choice 2, 32. Let me show you how to get it. The first step is to figure out the concentration of the substances. For the molarity of NOCl, it will be 20 moles over 4 liters, so the molarity is 5 molar. The next step is to set up the rice table. The initial concentration of NOCl is 5 molar. In the question, we are not given the initial concentration of the products, so they are 0. Since they are 0, the reaction will shift product side. The change of concentration for NOCl will be minus 2x. The change of concentration for NO will be positive 2x. The change for Cl2 will be positive x. So the equilibrium concentration for NaCl will be 5 minus 2x, for NO will be 2x, and for Cl2 it is x. In the question, it tells you at equilibrium 8 moles of CO2 was found in the container. So the concentration of CO2 at equilibrium will be 8 moles over 4 liters, which is 2 molar. Since CO2 at equilibrium, according to the rice table, is x, x is equal to 2. And since x is equal to 2, we can plug it in into the other ones as well. So NO is equal to 4 molar, and NOCl is equal to 1 molar. The next step is to set up the K constant equation. K is equal to NO squared times CO2 over NOCl squared. Next, you plug in the equilibrium concentration into the K constant equation. K is equal to 32. Try to do the practice question by yourself. Pause the video. Resume is completed. Here are the answers. This concludes the video lesson. Remember to do the homework.